So after solving for this differential equation using explicit differencing and realizing that we had certain restrictions based on our initial conditions, we want to look for another method where we can evaluate more freely. So this method is called the Crank-Nicolson method, and it'll just allow us to evaluate this without any restrictions. So the first step is going to be to make the approximations similar to what we did in the explicit differencing. So for partial differential of temperature as it has to do with time, we'll get T j n plus 1 minus T j n over delta T is equal to alpha T j plus 1 n minus 2 or minus 1 plus 2 u T j n plus T j minus 1 n all over delta x squared. And so this is what we had for the explicit differencing, and that was the end of it. But for Crank-Nicolson, to make this a little bit more accurate, it's going to take the average of these positions at time n, as well as these positions at time n plus 1. So what we're going to do is take all these same positions at n plus 1 and add it to this. So that gives us T j plus 1 n plus 1 minus 1 plus 2u T j n plus 1 plus T j minus 1 n plus 1 all over delta x squared. And since we're taking the average of these two, we need to divide by 2. So I'm going to go ahead and put that out front. And now the first step I want to take is to get all the constants together. So the constants that we have will be delta t, alpha, 2, and delta x squared. So I'm going to put those all over here. So I'll just erase. And that'll be equal to alpha delta t over 2 delta x squared. And so this will be our jumping off point to get our final equation to code. So first, we want to combine all the n plus 1 terms on one side and all the n terms on the other side. So we're going to do all the n plus 1 over here. But before that, we want to simplify this term right here, as we did with r in the explicit differencing. So we're going to call this u and substitute u in here. So after moving everything over, we'll end up with negative u T j plus 1 n plus 1 plus 1 plus 2u T j n plus 1 minus u T j minus 1 n plus 1. And this is going to be equal to u T j plus 1 n minus 1 plus 2u, or rather this is going to be plus 1 minus 2u, tj n, plus u tj minus 1 n. So this is going to be our final equation for what we put into code. Although we have a lot of unknowns, the way that we'll set up the Crank-Nicolson method uses a matrix, and as well as what's the word I'm looking for? It'll use a matrix of the u values and a vector of the t values to be able to evaluate this at any time t. So now that we've derived this equation above, we want to take a look at how this bar would look actually visualized. So we're going to have this cut up into increments. And first one's obviously going to be t sub j is equal to 0, t1, t2, so forth, all the way up until tn minus 1 and tn. And we know that this t0 is always going to be equal to 50 degrees no matter what time, and this tn is always going to be equal to 8 degrees no matter what time. So what we want to do is to create a vector of these temperatures that we can multiply by a matrix in order to make use of all of these variables to solve our equation. So, first thing we want to do is create a vector of the temperatures. So I'm going to start with T1, T2, T3, etc., down to Tn minus 1. And so this is going to be our vector of T sub j. And these temperatures are coming from this left-hand side, so these are all going to be at T is equal to n plus 1 delta T, because these are all going to be at the time interval n plus 1. So now what we want to do is take a look at what the coefficients will be here. So for T2, let's do that one first, we'll have coefficient of negative u, 1 plus 2u, and negative u. So those will each be multiplied by our t values along the vector. And then we can do the same thing for T3, negative u, 1 plus 2u, negative u. As these t values shift, so will these u values, or so will the u values. So what it's going to end up creating is a sort of diagonal of these u values that will go across. And then down here we'll have zeros. And this is how we'll create our matrix. So this is going to be our matrix. And it's going to be, draw the lines. We don't get confused what line is which. So now that we've drawn out the left side, we want to continue on the right side. So the first step will be this u. Or let's start at T2 actually, as we did before. So T2, Tj plus 1 is going to be u T3. And that's going to be 1 minus 2u T2 and u T1. And as you can see, that's what we would have from the equation. And these are all unknowns. But if you look at T1, there's actually something that we do know. So at T1, we're going to have u T2, 1 minus 2u T1, and then we're going to have this T0 value here. But T0 doesn't depend on the time. We know it's always going to be 50. So what we're going to do is, at this Tj minus 1 at T1, this is also going to be T0. And because it doesn't depend on time, we can go ahead and move this term to the other side for T1. So what that's going to do is make this 2u T0, as you can see there. We'll go ahead and close up that bracket. And now, if we go to the other side for T1, we can do the same thing. So we know we're going to have 1 plus 2u for the T1 value, and we're going to have negative u for this Tj plus 1 value. But what we're not going to have is this Tj minus 1, because at T1 we've moved it to the other side. So this is going to be our matrix. And this is what they call a banded matrix, because you have this band of values that will travel at a constant diagonal across the matrix for any values of t. And so now we want to look at what the right side is for Tn minus 1. Because, like for T1, we know some of the values for here. So at Tn minus 1, we know that this is going to be 2Tn, because Tn is going, or this is 2UTn rather, because we know Tn is always going to be 80. So we can move the Tn from this Tj plus 1 over to the other side and get, or rather we move this one over to this side and get 2UTn. And then we'll have 1 minus 2U Tn minus 1 and U Tn minus 2. So this is going to be our final matrices and vectors. And of course, this is where the equal sign is. And all these times over here are at t is equal to n delta t. So now that we have this matrix, we're going to take this into a collaboratory and evaluate the solution to this matrix to get our answer independent of initial conditions. So now we've moved on to the coding part of this problem, and as the same as it was with the last coding problem, we're going to start by importing numpy as np, and we also want to make another temperature profile. So we're going to, from plotly.subplots, import make underscore subplots. And then we're also going to make use of a banded matrix in this coding method. So we're going to go ahead and from scipy.integrate import solve underscore banded. So that's going to give us all the Python that we need. Oh, it's not scipy.integrate, it's scipy.lenout. That should be better. Okay, so that'll give us all the Python knowledge that we need to complete this method. So again, as with the last one, we're going to input our constants, ti, t left, t right. They're going to be 25 this time, still 50, and then 80 on the left. And so that's just a bit more of an efficient way to do it than we did the last time. And then we're also going to designate alpha, dx, dt, and those are all going to be equal to, let's say, 1 at the start. And then we also have another constant in this problem, which we called u earlier. So we're going to say u is equal to alpha times dt divided by 2 times dx squared. It's going to be actually divided by. So those are going to be all the constants that we need for this problem. And now we can move on to making our banded matrix. So again, we're going to have these time intervals n. That's going to be set to 20 because it's split up, or those are, sorry, the space increments on the bar. And there's going to be 20 of those as it was before. And again, we're going to make a range of x values, an n number of x values, and those are going to index from 0 to 19. So now we want to make the left side of our equation, or our banded matrix. So let's just call that a band. And that's going to be equal to, let's just make a 0 matrix at first of dimensions 3 and minus 2. And this is going to be n minus 2 because if you remember from earlier in the video, we moved two terms, which were going to be t0 and tn minus 1, to the right side of the equation. So that our left-sided matrix is actually going to be 18 18 spaces wide instead of 20. So now that we've done that, we want to set a band 0, 1 to the end is going to be equal to negative u. So that's going to be the upper diagonal of our banded matrix. And now we're going to say a band 1 from, or we'll just put a colon in there to go from the very start to the very end. This is going to be the center of our matrix, center of our banded matrix, and it's going to be equal to 1 plus 2 times u. And now we need to do the upper diagonal, and the upper diagonal is going to go, it's going to be the 2 for the upper diagonal, and it's going to go from the start to negative 1 before the end, because that's the term that gets moved over to the right side as well. And that's also going to be equal to negative u. So now that we've made our banded matrix, we want to make our vector of t values. So to do that, we're going to say, do the same as before, t equals np dot full n, comma, ti, where ti is 25 degrees, the very initial temperature of the bar. So now that we've done that, we want to say that T0, which is the left of the bar, which should be set constant to 50, and T n minus 1, that's because Python indexes from 0 to n minus 1, are going to be equal to 50 and 80. So now that we've done that, we want to make our subplot. So fig dot make underscore subplot in parentheses, and then we're going to put in what we want our x values and our y values to be. So to do that, we're going to do fig dot add underscore scatter, and our x values are going to be equal to x. Our y values are going to be equal to t. And we're going to do the same as before. Mode is equal to lines, and we're going to go ahead and put in a name for that initial value, and that's going to be equal to f string 0. So this is going to give us the scatter plot that we want, and this is going to be the very initial temperature profile. So let's see what it didn't like. MP is no. Oh, should be zeros. And what else? Name fig not defined. Let's see. Oh, this should be fig equals make subplots. We'll have to figure out why this isn't working, and I'll be right back. So it turns out the only issue was that instead of make subplots, I forgot the P, so I said make sublots. So now that I have the P in there, we can see our initial temperature profile of the bar. But we want to see how it changes with time, so we're going to make another loop to see how it changes. So for I in range, let's say 1 to 1,000, which is what we did in the last coding problem. And now we're going to specify the right side of the equation, which I'm going to call some function b, because that's what Python likes to call it as well. So b is going to be equal to, and if you remember, there are a couple terms on the right side that are kind of strange. So I'm going to go ahead and type this out and then tell you what's different about it, or why it's different. So I'm going to start t from 2 to the end plus 1 plus 2 times u times t from 1 to negative 1, which will be the end, and then plus u times t from the start to n minus 2. And so the reason that this is a little bit strange and why some of these don't start at the beginning or end at the end is because if you remember in our initial equation, we had some terms from the left side of the equation move out of the banded matrix and onto the right side. So those are not going to be consistent with the rest of the range of the right side hand values. So now we're going to specify what those initial values are now. So B0 is going to be equal to E0 plus U times T0. And this is because we have an extra U times T on the right side, which came from the left. Okay, so now we're going to specify the last term of B, which is going to be B negative 1, which is the current last term, times U, or plus U times T negative 1. So it's going to look very similar to what the first term looks like because it also has an extra U times T. But this one is to the negative, is negative 1 instead of in 0. So now that we've done that, we want to specify what T is, because that's what we want our actual Y values in the graph to be. So T from 1 to negative 1, so the whole thing, is going to be equal to, and this is where we're going to bring in our banded matrix. So Python has this really cool function called solve underscore banded, and it'll basically solve any banded, it'll solve, like if you input a banded matrix on one side and you input what the right side is equal to, it can solve the banded matrix for you, even if there's like way too many unknowns as in this problem. So this matrix, we're going to start by saying there's one upper and one lower diagonal, just telling them the exact dimensions of the banded matrix. And the banded matrix name is going to be A band, and the right side name is going to be B. So that's going to be what our temperature values are. So now that we have those, we want them to be updating into the scatter plot. So we're going to make another loop, this time an if loop. We're going to do the same thing as we did last time. We're going to say if the remainder of I divided by 25 equals 0, or is equivalent to 0, then we're going to add to our scatter plot, where x is still going to be equal to x because those values don't change, and y is going to be equal to the t values that will consistently update as this loop is run. And we're going to keep the same mode of lines, and we're going to name it something a little different this time. This time we're going to name it I times dt. And so this means that our labels will actually be what the time is at the current time. Excuse me. So close that up, and now we want to display our chart a little different. I like the dark background. So fig.update underscore layout. We're going to say the width, let's do 800 because that worked for the last one. Or this, yeah, width is equal to 800, height equal to 600, and we're going to do template is equal to plotly underscore dark. So let's see if this did what we wanted to do. Invalid syntax. Oh, this should be a comma instead of a colon. I believe I did that last time. Object has no to scatter. This should be an under. Oh, should that be an underscore? Oh, it's fig.add_scatter. That's what I'm doing wrong. Array must contain. Okay, let me figure out what this error is, and I'll be right back. Okay, so fortunately I was able to figure out the answer or the problem pretty quick again. So right here you see I have 1 plus 2u. Well, that makes it just constantly increase. So it needs to be what it's actually supposed to be 1 minus 2u. So now that we have that, this will give us a very nice temperature profile. And you can see it already goes till steady state. Let's make it to say 700. Okay, that'll give us a little bit more room to work with. We'll say 20. That'll just give us a couple more closer to the original value. But now we want to see if we can truly use any DT values for the Crank-Nicolson method, which is the whole reason that we use this method. So we're going to change DT to, let's say, 10, and you can see that it gives us our temperature profile. We need to add a lot more. Let's say, oh, well, that's not what I wanted to do. And let's see if we can make it smaller too. Let's say 0.1. So as you can see, when we use 0.1, we don't quite get to the steady state, but you can see it does the same thing. So we have proven that the Crank-Nicolson method and implicit differentiation can actually solve this without any restrictions on the initial values.